Welcome to the course. This is the second part of a suite of 4 courses covering computer architecture, organisation and design. Now, in the first course, we designed a simple 8-bit machine. We had a fully hardwired control unit, and from this control unit we generated our own instruction set. We also generated an assembler and a simulator. So we could write programs in our own instruction set in the simulator, and we can test to see whether it worked. Now, when we got it working, we could take the output from that simulator and we could put it into our assembler. We could then assemble that to get the actual machine code and then load it into the CPU and actually see it running. Now, that 8-bit machine was quite limited. So what we want to do is take that simple design from the first course and extend on it and make it an awful lot more powerful with a lot more functionality. Now, the first thing we're going to do is look at how we get information into the CPU and out of the CPU. So we're going to first of all look at something called port mapped I/O, and we will generate a few extra commands which will make it more efficient getting information in and out, and it will simplify our design. Now, once we've done that, we really want to take the machine and make it a 16-bit machine. So we will expand on it and we will change our 8-bit machine into a 16-bit machine. Now, once we've got that 16-bit machine, we want to expand on the instructions. But in order to expand on the instructions, we're going to have to redesign the control unit. The control unit as it stands now is purely hardwired. So if we try to expand that to an instruction which is going to be 16 bits and an instruction set which is going to be an awful lot more complex, then doing it in a hardwired control unit is going to be very difficult. So what we want to do is take our hardwired control unit and generate a micro-coded control unit. We will also see that what we really want to do is find a happy balance. We want the control unit to be part micro-coded and part hardwired. And I've actually designed that control unit very carefully in order to make the CPU as general purpose as possible. And it makes it a very useful learning tool. So it means that whenever we generate our instruction set, we can generate it in such a way to allow all of the registers to talk to all of the other registers. And by doing this, we can generate a very, very general instruction set. And we'll also be able to generate far more complicated instructions as well. We will also look at different addressing modes, and we can generate instructions using lots of different addressing modes. Now, another thing we will do is change the input-output in this device as well. So rather than using the port mapped I/O, we will look at memory mapped I/O. So we will cover that in this course as well. So once we've built up our new instruction set with all the new addressing modes, we still need to be able to assemble it. So I've generated an assembler in Python, and this is far more powerful than the simple Excel assembler for the 8-bit machine. Now, finally, what we want to be able to do is take a step up in the hierarchy. So we want to start off this course thinking about the course as designing a CPU, but by the end of this course, we will be thinking about, rather just having the CPU will be part of a computer. So we really want to generate a method of writing information into the computer and taking information out of the computer via a keyboard, a display, and a graphics unit. So we will integrate these units into our CPU, or what is now becoming our computer. So there's an awful lot to get through in this course, and I will be continually adding videos onto this course. So keep an eye out and come back every so often and have a look, because you will probably find a few extra videos and a few extra sections added in. So thank you for listening. Let's get started and let's get this done.